So they just asked me before if it was okay to tape it if I had anything that was unpublished, and I thought it was all unpublished because I'm on sabbatical here. I'm trying to do new things, and so it's a little bit of a different talk for me in that it's stuff that's ongoing. I have a couple more months here, but what I'll try to do is explain the idea of what we're doing and show some of the initial results. And obviously, being on sabbatical, I've had a lot of chances to interact with some great people, and I just wanted to acknowledge some of them here who have taught me a lot, and it's been fun to work with. I should say that it's my sole responsibility to have a word like climate in the title. I should say this agreement to host me was done before the government decided that the word climate should be banned from all funded proposals. So I take full responsibility for that part of it. But let me also explain a little bit of the idea of the visit here with Scott and Graham and the group, and what the idea of this idea of climate adaptive traits, because it kind of is an odd concept, especially for somebody who's used to thinking about crop development. We think, well, we always adapt crops to the climates they're in. That's just what we do. The idea here is a little bit more specific about trying to think about how do we adapt crops to the changes in climate. And with climate change, kind of the novel aspect is that it's a moving target. We have constantly changing environments in the places that we grow food around the world. And this is something we expect to continue to change for the foreseeable future. And so the very general basic question is does that change how we approach crop development? Is there just more of the same and that'll naturally deal with these changes, or do we do something inherently different? And this is a different kind of question than I'm used to. A lot of the stuff I've done that Graham mentioned on climate change is more or less the good or bad type question, like how good or bad is climate change for this particular system? What are the risks associated with climate change? And those kind of questions are certainly useful in a lot of settings, especially when you're trying to figure out as a society whether it makes sense to cut emissions or keep burning away. You want to know what different climate scenarios would mean to agriculture. But this is a different, more specific question of how does a certain community, like the crop development community, how should they be changing what they do, or should they just keep doing what they're doing and ignore all of the discussions about climate change? So I'll try an analogy here if that wasn't clear with my showing off my newfound expertise of cricket. But if you're a batsman in cricket, that's the right word, right? Batsman, not that. And you have a new bowler coming into the game, let's say a fast bowler, you could probably spend a lot of time thinking about, oh boy, is this a good thing or a bad thing? Is this going to, change my odds? Or think if you're the coach, not the batsman, does this change the prospects for the game? Is this going to be more likely or less likely to get runs or get a wicket or whatever? But on the other hand, you might also think very specifically, okay, does this change what I do? I mean, am I just going to go up there and try my best, or do I take a different stance? Do I have a different strategy in terms of how I swing? There's all sorts of examples throughout sports, but cricket would be one where there's this risk management game. If you don't know exactly what you're going to get, you know sort of the general nature of the beast ahead of you, and you have to decide what's your strategy going forward. And is it a different strategy with this particular bowler or with climate change than it would be just in a normal situation? Now, I'm going to, so this is for the people who think more sort of visually, is how I often describe it to a policy audience in general. When we think about adaptation, it's useful to think about the fact that there are all sorts of decisions within agriculture, within crop development more specifically, that make sense regardless of whether climate change is happening. And you can spend days and days people arguing back and forth, well, this should be our priority, and let's call it climate adaptation because there's billions of dollars going into climate adaptation, and it still is the thing we should be doing. And that's all well and good. But what's really interesting is to try to think about what are the things that we should be doing that we wouldn't have had to do, or we shouldn't have been doing if climate wasn't changing, or what are the things that we shouldn't be doing anymore even though we would have done them in a world without climate change. And it's not all that, I'm drawing these sort of very schematically, it's not all that clear how big these parts of the circle would be. Again, is there anything truly different in terms of how we approach the problem? In particular with climate change in crop development, do we prioritize particular traits differently than if we weren't concerned with this moving target. So that's the kind of thing that we are thinking through in very specific terms in specific crops. And I will spend some time today knowing that only about half the audience is really, from a crop perspective, explaining what the particular trade-offs that we're thinking about in terms of particular traits are. And so the what I'm calling grain expectations is what just kind of intuitively do we expect to happen to grain yields given certain traits in the environments and the types of changes in the environments that we're thinking about. And then in an effort at symmetry, I've titled the research results A Tale of Two, I couldn't use cities, but A Tale of Two Places that are feeding cities in terms of how Australian and Midwestern US systems are changing. You can see this is like the 6th or 7th talk I've given in Australia. I keep trying to figure out what makes an Australian audience laugh, and I haven't been successful with any of my American humor. So I've gone to, I figure, I don't know much about New Zealanders. You could always make fun of New Zealand. You make fun of Tony Abbott, or you have plays on words, and so that was my attempt here. Okay, so with yield, grain yield, the part of the crop that we are most interested in, typically, apologies to the livestock folks here, but typically we're most interested in the grain part, not the fodder. And we often think of that as a combination of two pretty simple factors. How many grains do you have in a plot of land or on a particular plant, and how big are those grains? Okay? And the reason we like to decompose those is because it helps think about the process of crop growth and development, and there's distinct phases of the cycle where these different things are determined, and we can often explain a lot of variation based on one or the other, different crops in different ways, and I'll explain that. So if we have crop growth throughout a season, from the beginning of the cycle, plants grow, then senesce. We have the vegetative period. We have this period around flowering, which is known as the reproductive period. Then we have the grain filling period towards maturity when these grains. So you can see here in these black, this is example from a wheat system, but you'd see something similar in a lot of places that most of the biomass initially is in the leaves and the stems. This is above ground biomass, so Vijaya can tell you there's all sorts of stuff going on below ground, but we tend to, to not have that data. So this is just data from above ground. Leaf and stem, and then around, or before flowering, you start to get the spike coming in. And then when these grains get set, then they spend the rest of the time getting filled. So that by the end of the season, a very large fraction of the biomass is in grain, up to half, typically. Now, what's interesting about the crop cycle is that there's some overlap, but in general, grain number is going to be determined for, say, the month or so leading up to the flowering period. And the grain weight is going to be determined for that window subsequent to that overlapping, but into the grain fill period. And obviously, the grain fill period is going to be really important for the grain weight. But there's also some, as I show here, there's some periods of what I'm calling broad sensitivity. So in the case of grain number, what's really important is overall the growth rates in the month leading up to flowering. That will be a very key factor in the plant's determination of how many grains it should set. And similarly, the broad growth rates over the grain fill period is going to be very important for overall how much carbohydrate is available and going into these grains. But there are also periods of what I'm calling more acute sensitivity, in particular towards the earlier stages and even slightly after flowering, acute sensitivity that could affect the grain number. And then right after flowering, there's also a lot of issues with shocks to the plant that can occur that kind of irreparably affect the amount to put on to have big grains itself. So there's this question of broad sensitivity in both grain number determining period shown here and the grain size determining period, and then there's acute sensitivity. And both of these broad kind of growth rates and these acute, more direct effects of heat or drought stress on the plant, apart from the growth rate effects, these can occur because of either drought stress or heat stress. And hopefully it'll become clear throughout the talk why I'm using these terms differently. Obviously, on a hot day, you can get a lot of drought stress. On a dry day, you can get a lot of heat stress. It's not that these are completely unrelated issues. And in particular, as I'll describe, heat stress can drive a lot of, or high temperatures can drive a lot of drought stress. But when we talk about heat stress, we're really talking about physiologically the effects of the temperature being the thing that's causing the plant to respond, versus drought stress where it's physiologically the effects of lack of water causing the plants to respond. You can think of it that there's a bit of a false dichotomy here, but it is different physiological processes and different aspects of the plants that are affected. And so it's, as we talk about climate change, they're affecting both of these things, and I'll talk about that. Now, I've talked about how yield is grain number or grain number times grain weight. And an interesting question that's been looked at a lot throughout different crops in the literature is which of these is really more important? Is it more important to get that growth rate right leading up to the grain number? Make sure you have lots of grain numbers. So when you're, for example, screening crops or looking for traits, do you really want to look at grain number, or do you want to look at grain weight? And it depends on the crop. This is a summary of a lot of different data, including some that I think Scott did a while back, looking at variations in maize yield around the world, both in tropical and temperate systems, and variations in the grain numbers on these, in these areas. And you can see there's a huge amount of the variation in grain yield is associated with changes in the grain number. So maize, wheat would be a similar crop where a lot of the yield variation can be explained by the grain number part. The grain weight tends to be fairly constant across lots of environments. But there are variations known to exist, and this is again for maize, that you can get variations in grain weight, and particularly if you're growing in the grain fill period under particularly bad conditions, you can have grain weights that are below optimal, and you can get some yield variation explained by grain weight, but by and large, it's mostly grain number. In a crop like sorghum, it would be much more weighted towards the grain number than much more weighted towards the grain weight than a crop like maize or wheat would be. And then for each crop, it'll have its own story. So it's not a simple answer, well, focus on grain number or focus on grain size, as you might, it's not really surprised that it's not a very simple answer. These are crops after all. But it's important to keep in mind this trade-off between trying to minimize stress during the period where grain number is going to be determined and trying to minimize stress when grain weight is going to be determined. OK, so enough of the generics. Oh, maybe not quite enough. Let me just talk more not only about the trade-off between the timing of the stress, but the trade-off between the drought and the heat stress. Because you could see that the benefits of, say, using up water is that you reduce drought stress, obviously. If you're using up water, you have plants, say, that are more vigorously bringing up water from the soil. That's going to minimize the amount of drought stress in that particular point in time. It might set you up for drought stress further on in the season if you're exhausting the soil water. But the other thing that water use is really important for is for determining heat stress, because as you're using water, you're then transpiring as a crop, and that can have important effects on the heat stress. So there's trade-offs between how much do you worry about saving water for reducing further drought stress in the future versus using water to avoid heat stress, or you would also avoid then heat stress potentially in the future versus using it now to avoid heat stress. OK, so there's trade-offs in time. There's trade-offs in terms of the types of risks that you face in any point in time. And this is just I think Scott showed this in terms of explaining that the water is leaving mostly the system is leaving through transpiration, and that has an important cooling effect on the canopy. OK, so now into some specific examples before I get into talking about our research. So this is something that both Graham and Scott have talked about already. So those of you who were there know this particular trait, which is what's known as the max TR trait. And the idea of this trait is that in the time of day, so this is a plot of the vapor pressure deficit as a function of the time of day. So in the middle of the day, you have very warm air, potentially very dry air, really sucking water out of the crop. You can think of it that way. So this is the time of day when you have the least efficient use of water, because the atmosphere is so hungry for water that if you are going to continue to grow as a plant, to continue to take up carbon, you're going to lose water at a very fast rate during the middle of the day. So there's a particular trait that's drawn a lot of interest, which is, well, what about plants that are very strategic in the sense that they can grow as fast as you like until you get to a certain VPD. And at that point, you just can't transpire any faster. There's limits to how fast that particular plant can transpire. So you cap your transpiration rates, say, you can choose a rate. This is showing a study from Thompson, Clare, and Graham that was from a while ago, where they explored different ways of capping this. Now, the benefit of this is that you're not losing all of this water at a time of day where the amount of growth you get back for that amount of water loss is a pretty poor return. So you're saving that water for cooler times of the season or cooler times of the day where you can grow more efficiently for that same amount of water. So that seems like a good trait to have. On the other hand, what's going to happen is as you shut down transpiration, your canopy is going to warm up. And there's all sorts of effects of high temperature on canopy. And this is just an example from, again, work done here with Graham's group. And this was a whole host of authors looking at the effects of high temperature in sorghum itself. This is just showing you the seed set up to 100%, actually up to 120%. I don't know how you get that. But this is the amount of seeds that are successfully set or successfully pollinated. And you can get, these are different genotypes, so there's a lot of variation. And it's comparing the amount that occurs at 32 versus 38 degrees daytime temperature. And so you can see there's large effects on average, especially in the left, these genotypes. But even here, there's large effects of exposure to very high temperatures. So what I'm glossing over here is the difference between, say, the canopy temperatures and the temperatures of the individual spikes. But in general, and this has been known throughout different crops as well, there's going to be effects on canopy temperatures which spill over to effects on the seed temperatures, which could potentially affect the set of the grain. And if you have low grain number, even then for the rest of the season, if you've saved all this water for great growth, you're going to be potentially at a disadvantage. So here's an example of that. We don't know how important in general these trade-offs are, but this is what I think is a pretty interesting and compelling example. And what they did here was they are looking at varieties that do well under drought. And this is kind of typical drought. How you would typically test drought traits for a crop is you would water them for a little while, have a control that keeps getting water, then you have another plot where you turn off the water. And you're testing, in a relative sense, how well those plants can survive water stress. But typically these are done under normal conditions, and very rarely do these experiments occur in a year in a place where you would get exposure to very high temperatures. So what they also did in addition to those kind of experiments is they did some experiments where they intentionally tried to introduce high temperatures, usually by planting really late. And then they test how well did the varieties do in those ones that were exposed to high temperatures and drought. And what happens is that you can see here, these are just showing the correlations between the performance of particular lines. You can think of these, plants there are lots of different traits associated with each of these individual lines, but these are correlations of the performance in different conditions. So this would be, say, a correlation of 0.63 between their performance in the constant irrigated trials versus the drought trials. There's about a 0.49 correlation between the ones that were just exposed to the high temperatures versus the ones that were exposed to drought. I don't know if I said this. This was for maize, yes. It says down here. And what you see here is that there's a very low correlation between the performance when you just have low soil moisture versus when you have low soil moisture plus very high temperatures. And again, the idea here would be that, well, your benefits of saving that water were really much smaller when you had high temperatures to deal with, especially around the flowering time. Now, they don't have a whole lot of discussion here about what particular traits were associated with the ones that did well here versus the ones that did well here. But you can see that essentially there's no relation. If you knew that a plant did very well under the low moisture conditions, you wouldn't actually be able to predict very well how well it did under the high temperature, low moisture. So if nothing else, this is hopefully proof that these trade-offs can be quite important and quite important to figure out how these environments, how these relative risks are changing in different environments. Okay, so that was kind of the point of all that, is to explain that the relative value of, say, using water in a particular setting or saving water or other traits associated with drought or even heat for that matter are going to depend on the particular environment. And the challenge now, as I said, with this moving target is all sorts of aspects of the environment are changing. So this won't surprise anyone. One of the big aspects that's changing is CO2. And this is just a plot of historical CO2. This is very smooth, not showing the seasonal variations. And projections out to the end of the century, you can see that So these projections have different assumptions about how our energy system evolves and how our economy evolves over time. And they don't diverge all that much until you get about 2040 or 2050. And they diverge from something that is on the order of, say, merely doubling what pre-industrial values were to more than tripling what pre-industrial values were. So very large changes in CO2, and you all know that CO2 is one of the major elements of plant growth. It's fixing carbon. As you raise CO2, you tend to increase the rates at which plants are available to fix carbon, especially C3 photosynthetic plants. So this is, by itself, a very important effect. In addition to that, though, what happens as you have high CO2 is plants tend to close their stomata, which saves water. These were concepts that have been discussed in prior sessions as well. And one of the effects of that is, again, that you raise canopy temperatures. And this is just an infrared image of some of these high CO2 field experiments where you can see over the high CO2 areas, you get temperatures that are a degree or more above what they are in the same conditions except for lower CO2 outside. And again, just as an illustration of how these heat and, in a sense, drought. So if you have high CO2, one of the things you do is you directly stimulate photosynthesis. You also alleviate drought stress because you have become more water efficient. So this is a study that was done some time ago in Japan showing the percent of seed loss, or actually this is the percent of successful seed set in rice versus the experimental temperature at two different CO2 levels. And what happens here is that although CO2 on average is a big benefit to rice, what happens at these high temperatures is you actually start losing grains at a lower temperature with high CO2 because of that canopy feedback effect. So you have CO2 changing, which is going to change the drought characteristics of a system. It's also going to change the propensity to get extreme heat. Okay, then we have kind of the big consequence of the high CO2 is the higher temperatures in the atmosphere. This is just an analogous plot to what I showed you for CO2, but now showing projections of average global mean temperature. These are global mean. So in the US, I have to usually first emphasize these are degrees Celsius, not degrees Fahrenheit. But the more important distinction actually is that these are global means, so the oceans are 3/4 this number. So the warming over land, or in particular over places where we grow food, would be quite a bit larger. But you're going from anywhere on the order from as low as 1 degree above late 20th century to as much as 4 degrees. This is the average model projection. Some of them get quite a bit warmer, and then some obviously cooler. Now this obviously directly affects so I'm going to kind of just do the opposite of what I did with CO2. CO2 is kind of obvious that it'll affect the drought stress, but it's not quite as obvious that it'll affect the heat stress. Well, with heat going up, it's quite obvious it'll affect the heat stress, right? But also it has maybe some less obvious effects on the drought stress. And in particular, what happens as you warm up is you increase the saturation pressure of the air. This is a very well-known result from chemistry, really, that, or physicists would say from physics, that as you raise the temperature, you have a nonlinear increase in the saturation pressure of the air. So for a given relative humidity, which is shown with these lines here, as you warm up, the difference between saturation, which is basically what the leaf is at, and what the air is at, is going to grow. And so that vapor pressure deficit can really, really increase quite rapidly as you warm. So just showing as an example here, if you go up 10 degrees Celsius at a relative humidity of 60%, your vapor pressure deficit nearly doubles. So temperature is going to not only affect the heat components, but it's going to very much affect the drought components. And I'll, with examples, explain that in a little bit. Now, another element of global change that's often not appreciated is humidity changes. Because, again, vapor pressure deficits depend on humidity, and drought stress is going to be really affected by changes in humidity. And actually, the projections for humidity around the world are really non-trivial changes in a lot of the cropping areas. So globally, the theory has been that relative humidity would stay fairly constant. As you raise the saturation pressure of the air, generally you raise the absolute humidity of the air. And that's true in general. But actually what you see is that the oceans are, in general, increasing slightly in relative humidity, and the continents tend to decrease in relative humidity. So this is showing something for what I used to call summer, but now I'll just call June through August. In the US or in Europe, that you have, this is their cropping seasons, and this is something where you get on the order of a 10% reduction in relative humidity by by the end of the century. So maybe you're not used to thinking about relative humidity, but that's a pretty big change in relative humidity. And if you cut that in half for mid-century, that's still a pretty sizable change to think about. You'll notice the changes in Australia aren't quite as big. They exist, but they're not quite as big. The dots, don't worry about for now. But I'll come back to that later, because that is one distinction in these two places that I'll talk about. OK, and then, of course, we have rainfall changes associated with climate change. These are generally, I would say, small. I would say they're uncertain, but they're quite small. But regionally, they can be important. And this just shows you kind of the general global pattern of what happens with rainfall on a per degree of warming, because it scales, again, because the ability of the air to hold moisture scales with the amount of warming, that actually a lot of the precipitation patterns you see globally are more related to the global temperature increase than anything else in terms of how you can explain differences between different models. So models that are getting very wet are often the ones getting very warm in a global sense. And you can see that there's a band of drying around subtropics. Unfortunately for Australia, they sit right in the middle of that. And then particularly for the Mediterranean and the northern hemisphere, they sit right in the middle of that. And increases of moisture in the very high latitudes. But lots of uncertainty around this, which I'll come back to. OK, so you have all these components going on in the climate systems, all these changes in the environment going on. And then you're trying to select crops. You're trying to select crops for traits that have potential benefits in some situations, potential disbenefits in other situations. OK, so hopefully by now at least you're convinced that there's not obvious which traits you would want. It depends on which particular environments you're in. It's not always good to go for, say, drought tolerant traits. It's not always good to go for heat tolerant traits. If it were, I mean, maybe the jobs of breeders would be less interesting than they are. There's all sorts of G-by interactions that have been discussed throughout this whole seminar series. These risks depend on several of the factors that are changing around the world. So there's not an obvious answer. And it may well differ depending on the particular crop, their particular sensitivity to heat and drought stress, the particular changes going on in the environment in the place they're on. OK, so this is all maybe a long-winded way of explaining why this is not a simple question, why this was something that I thought 6 months at a place that was really thinking about crop physiology would help me think through these things. OK, so where to now? So I mean, one of the options I had was just to kind of stand up here and pretend that I know the answer about where we should go exactly. But like this cartoon suggests, we don't really know exactly what to do next. We have ideas about what things we need to look for. And that's what I'm going to talk about today in terms of how do we get traction on this problem, given these multiple trade-offs and these changing environments. And in particular, we'll be using a tool that's proven very useful for exploring G-by-E interactions, which has been, again, discussed, so I'm not going to dwell too much on it. But this APSIM model, which is applied for a wide range of crops and treats both the development and growth processes in a fairly, I would say, a fairly detailed way compared to a lot of systems. It's particularly good, in my view, at looking at issues of drought stress associated with high VPD and associated with root growth. It's not, and this is not unique to APSIM, it's not yet at the point where it's very good at dealing with the direct heat effects. So one of the things we've been working on is trying to incorporate some of these heat effects so we could look more explicitly at these trade-offs, which we've seen experimentally, as I showed you. We've seen empirically that selecting for drought is different than selecting for drought and heat, but you wouldn't necessarily get that out of a model like APSIM right now because those heat effects aren't all in there. So one of the things Greg and others have been trying to do is parameterize these models for some of these heat effects, and then we can play around with them and look at these trade-offs going into the future. OK, so the two places I talk about are two of the major grain belts in the world. Yeah, sure. I'll elevate Australia a little bit. I typically think of the US, South Asia, East Asia, Europe, but certainly this is a very important grain belt regionally. And I'll spend most of my time talking about that because that is, in a sense, what would be more interesting to this group, but also what we've been working on a lot. The US stuff, Graham and I have been doing some work on, and I'll mention at the end, but it probably won't have time to go into as much detail. But the reason I want to talk about 2 is partly because I think the contrast is an example of the kind of contrast that we expect and that we want to be able to distinguish between. So this is sorghum. It's grown throughout central and southern Queensland and northern New South Wales. You guys all know that. When we talk about drought stress in sorghum, we often, and this is based on the work that Scott and Graham and others have done, we often talk about characterizing environment types. And so this is just kind of a guide to what we'll be talking about, is that if you look at the water stress, and you can get this out of APSIM for a particular point in time or a particular week, say, you can look at it as a ratio of water supply to water demand. And if that ratio is high, you have little water stress. If that ratio is low, you have a lot of water stress. Demand being how much water you lose to the air for a desired amount of growth. And that desired amount of growth is depending on how much radiation you have. So this just shows you the black lines are the traces of those stress levels for different simulations in different places, different years. And then clustered into 5 groups. And this would be a cluster that has very low drought stress. So this is basically a no drought scenario, high values of this index throughout the season. Then you have various degrees of drought, various flavors of drought. You have the mid-season drought here, which bounces back. You have the mid-season drought, which doesn't bounce back. You have the late-season drought, et cetera. So we'll be looking at, and these are proven very useful for looking for traits for particular environments that you know are prone to, say, mid-season severe stress or late-season stress. You would want to, when you're looking for traits and looking at screening, you would want to be able to match the particular environments that those crops did well in to the particular environments that they're going to be exposed to. Okay, so the other thing to understand is kind of the scope of what we're doing. So this is 15 sites we're looking at throughout the region, and the types of changes that are going to be feeding into these simulations. So these are the climate projections summarized across all the climate models that we have access to. So there's now above 30 models that provide climate output. And the reason we look at lots of different models is because there's uncertainty, like with any model and any projection. And what this is just doing is summarizing the spread of those projections for each of these sites for different time periods. So the 2030s are going to be shown in green, 2050s in orange, 2070s in blue. On the left is shown temperature. On the right is shown rainfall. And on the bottom is shown essentially winter here, the winter season, and the top, which is really the focus for sorghum, would be the summer season. So what you see is warming, kind of unambiguous warming, at the rate of about, so this is the difference between 2030 and the 1990 baseline. So it's on the rate of about 1/3 of a degree per decade, which gets you to about 1.2 degrees over 4 decades. And then you see rainfall changes, the characteristic being that they tend to span 0. So there's some models showing drying, some showing wetting. That the bulk of the distribution in the south of the region is actually towards wetting, whereas the bulk in the north of the region is towards drying. None of this is particularly new from a climate perspective. That's been shown in analysis of the IPCC, et cetera. But this is useful for interpreting what we're going to see and for setting expectations. So you see uncertainties. You also see that the changes are unlikely to be bigger, very unlikely to be bigger than, say, 20% in absolute value in terms of rainfall change, which that is a big value, but unlikely to be bigger than that for any particular place. Okay. So now, getting to some of the results. So what we do is we run, for each of these 15 sites, we run the particular combinations of soils that are found at those sites, the particular combinations of management systems, and Scott talked a little bit about this. Actually, Graham did back a month or 2 ago, too, is that how they have different combinations of the rows that they tend to grow, the sowing densities that they tend to use. So we try to capture all of those realities in the model so that we're looking at the impacts on the actual systems that are employed, which sounds kind of obvious. It also is actually not what's usually done. Usually it's just some kind of theoretical management, which is probably outdated by 20 years and is set to be uniform across all places when, in fact, it's not. Okay, so we run these simulations across the appropriate management soils historically for 30 years, and then for these chunks as you go into the future, 30 years at a time. And we look at the simulated outputs of the model. In particular, we're focused here not so much, again, on whether it's good or bad for yields, but on what the particular stresses, frequencies are, and then what we haven't quite gotten to yet, but I'll hint at here, is what particular traits would be more or less advantageous as we're selecting in that environment, or selecting towards that environment, which the crops would face when they are released. So I'm going to step through here the individual changes, just so you understand kind of what drives the overall results. You have, let's just focus on this for brevity. You have, this is the no drought environment, ET1, recall. 1990s, about 30% of the site years are classified as having very little drought stress. If you raise temperatures but do nothing else, what you see is that low stress environment becomes less and less frequent. And this is because, remember, the high temperatures raising the drought stress by raising the vapor pressure deficits. And the high drought stress become more frequent. If you change the rainfall, that doesn't qualitatively change the picture very much. Even though you had that slight increase of rainfall to the south, you also had the slight decrease in the north. So the overall frequency in the region actually still, drought stress becomes more common, no drought becomes less common as you change both temperature and rainfall. As I said, these rainfall changes just aren't big enough to really, at the regional scale, overwhelm temperature changes by themselves. But then you add CO2, and actually the situation reverses. And this was a surprisingly strong effect of CO2 to us. But in systems like this, where it's frequently the case where saving a little bit of water will really benefit you down the line, the CO2 helping to save that water through the system results in a net decrease of drought stress. So increase in the no stress, decrease in these high stress outcomes. And so what I'll show you from now on is just going to be the combined effects of all these. But now you understand maybe why slightly counterintuitively you get a decrease in drought stress, even though you're tending to have a reduction in rainfall in parts of it and a very fairly rapid increase in temperatures. These were just showing you the average response averaged across all of the climate models. As I said, there's 33 climate models. So if you look at the distribution across climate models, it's fairly unanimous, not completely. 75% of the models show an increase in the occurrence of ET1. So 75% essentially are showing a reduction in overall drought stress on the system, whereas a few of the models, so about 8 or so, 7 or 8 of them show very small or negative changes in this, so a slight increase in drought. And this just shows you the relative increase in these frequencies over time. Okay, now let's talk about heat stress, because I mentioned that this is the questions here about trade-offs between heat and drought. So we implemented in the model these results from the experiment, essentially characterizing different levels of heat sensitivity that correspond to different levels of sensitivity that were observed, from the most sensitive to the more tolerant. So I'm going to show you results for kind of the sensitive group versus the tolerant group. The sensitive, or the susceptible, being defined as starting to really have losses of grains at 33 degrees, whereas the tolerant show losses at 3 degrees above that. And what you see there is, the qualitative picture is not surprising, that you have an increase in heat stress. But it actually increases quite a lot. That you're, by mid-century, for the susceptible group, you're getting well above 2/3 of the site years having heat stress. And I should have said, what we're saying heat stress is here is that if 10% or more of your grains are lost due to heat in a year. So that's saying that 2/3 or more of all of the site years have 10% or more of their grains getting hit by high temperatures in this particular susceptible group. In the tolerant group, the numbers in absolute sense go down, but even in the tolerant cultivars, you're getting 20% of these events in terms of 10% of grain losses. Now, the 10% is kind of arbitrary, but we thought that was something that would be kind of noticeable and kind of relatable to historical extremes in terms of what a large heat effect looks like. Okay, so heat stress going up, kind of unanimously, drought stress going down. And the net result to that is that the combination, so this is just a simple summary of the combination of heat and drought. And I'll just explain briefly what that means. So this would be a scenario where you are in this ET1, essentially, where you have very low drought stress. and you don't have 10% or more of your grains lost. So that is not that uncommon, which is why agriculture can, thrive here, or at least get by, is that you have plenty of years which are neither too hot or too dry. And that shrinks over time. You have a set of scenarios where you have drought but no heat, and that is actually the most common stress, or most commonly occurring stress within Australian systems, and that really decreases over time. So even though you still have some droughts, they tend to be much more the types associated with heat, which is that next category, which is the red category here, rather than the yellow category. And this orange category is you have no drought, but you have heat, and that, of course, grows over time significantly. So by mid-century, or even by the 2030s, you have much fewer droughts that are characterized by no heat. You have much more droughts that are characterized by heat, and then you have a lot of heat without drought. And the net change in the overall low-stress category is actually going down. So your overall stress level is going up because your drought stress is going a little down. Your heat stress is going way up. And as I said, the types of droughts you're having are changing, which is going to affect the kind of varieties that you would want to look for. All right, I said I wouldn't really talk about whether it's good or bad, but this just gives you a sense of the net yield changes associated with those stress levels. And it really does depend on whether you assume you're very susceptible or not to those heat effects. The heat susceptible lines, again, the color schemes are the same, so 2030s, 2050s, 2070s. For a lot of these northern sites, especially the hotter sites, you have net decreases. Even though your drought stress is going down, you have net declines in yields because of these heat effects kicking in. There are uncertainties driven partly by the local rainfall changes, but the bulk of expectation is towards declines. Whereas if you are more tolerant of these heat effects, you would basically break out even throughout much of the sorghum belt, and you would be net positive here because you have the increases in rainfall that we talked about before. That's largely what's driving it. Okay, I'm going to move on. We can always come back with questions. Another way of thinking about this is what's the average yield loss due to stresses? And I've just shown here the average yield loss due to drought stress. In current climate is estimated at about 29%. That goes down. As I said, drought stress goes down. It still remains by far the most common source of yield loss, but it soon becomes rivaled, especially if you assume susceptible cultivars, it soon becomes rivaled by the losses due to direct heat effects on the plants. So right away you can say that this is setting up a scenario where you'd want to prioritize moving to heat-tolerant varieties more than you would if you were stuck in the 1990s climate and you didn't really have to think about potentially moving towards scenarios where your heat losses are doubling. Okay, a few minutes on U.S. I promise I'm done soon. So the U.S. is a system similar in a lot of ways, but different in some ways. This is showing you the main grain that we grow is just corn. Mostly it's rain-fed. It has years where it gets severe drought stress, or what we in the U.S. call severe drought stress. I don't know if Australians would consider it severe. But this was in 2012 where a lot of the corn fields were completely decimated by a combination of drought or heat. We don't really know how much of each. So to cut to the chase, one of the differences in the U.S. is that the rates of warming are a little bit faster and the rates of humidity changes are quite a bit faster. So actually in the projections in the U.S. are for more drought, whereas in Australia we were seeing less drought. And this just gives you some intuition behind that, or some kind of the changes in VPD, which would help explain that. So in Australia, by mid-century, we're expecting on the order of, say, a 5% increase in VPD, whereas in the U.S. we're expecting something more than double that. And when you run through the simulations, the effects of that are that drought stress actually is going up in the U.S. So again, that would maybe lend you to more prioritizing things focused on drought. However, that drought is also going to be hot drought as opposed to kind of the run-of-the-mill drought where you lower soil moisture and see how your lines do. So there's implications for traits that we're getting into, especially with this max TR traits. So I just said this, drought stress expected to increase. On top of that, management trends, which I haven't talked about today. I talked about that a little in the talk I gave the first month I was here. Management trends seem to, especially the densification of these systems, tends to really be exacerbating drought stress. But direct heat stress, I think, is still increasing quite fast in the region. And again, the challenge here is to think about, well, does that really change what we're doing? And I think the answer is yes, but we haven't yet got to the specifics of exactly what should you be screening for that you're not. Heat is kind of the general, but in terms of what particular traits do you want to look for? We know that a lot of the heat effects are via drought effects, but we also know a lot of them are direct heat effects. Okay, so for concluding, it's more I think the general notions that I want you to come away with as opposed to these particular numbers. One is that these target environments that we have kind of developed institutions in to think about and to breed for are changing over time in ways they haven't changed historically. And I think we're first really understanding the ramifications of that. The simple answer would be to, well, the systems adjust, but again, and maybe I didn't emphasize this enough, there's lots of lags in the crop development system. So if you are screening for things and then 10 years later the crop is released, that's going to be exposed to a difference. So you want to try to get ahead of the curve. And not only that, but some of the stresses you expect to be more common are really not implemented into screening trials now because they're not that easy to, like imposing heat stress is not that easy to implement in a large screening trial. So what kind of particular traits are you looking for as opposed to what you do now? In such systems, and it seems the Australian falls into this category, at least the Australian summer systems. I don't know if any of you were looking at the bottom half. The winter systems tend to actually have a bigger drop in rainfall, and so they may be a case where drought stress is likely to increase. And those simulations are underway. But in the Australian summer systems, it looks like drought is set to decrease, but in the US, it's the opposite. In all these systems, the fractions of drought that are kind of what I would call old-fashioned drought are quickly declining, and the new drought is the drought combined with a few punches of high heat in the critical periods. And if you're saving water in those periods to be smart about drought, you end up looking really silly when you don't have any grains to fill during the grain filling. And then finally, as a very general notion, and this is still kind of a working hypothesis, and as much as I said, I could pretend to know that we really should drastically rethink our whole breeding operation. I don't think that's the case. I think the working hypothesis is that we really should think through these shifts and how they implement the operations of crop development. And that first slide I showed with sort of how you think about adaptation, what decisions are we actually making, and which fraction of those do we actually need to do differently. I think it's a non-zero fraction, but we still haven't sorted that out completely. But in general, we don't. It's worth doing our due diligence and not spending a lot of time thinking we're hitting the right targets when in fact we're aiming at the wrong targets. So with that, I will end it, and maybe we have a few minutes for questions.